Swayam Prabha. Digital India. Educated India.
Welcome you to the next class on inorganic chemistry of life, principles and perspectives. The last two classes we have been looking at the molybdenum based enzymes, and we will continue with that and try completing the molybdenum based enzymes in this particular class. Okay, I already explained to you nitrogenase aspect complete, then started with oxidoreductase properties of the enzymes. These are nothing but the pterin containing cofactors, molybdenum cofactors. The cofactor that is present in nitrogenase is called the IFE-MOCO, it is called iron molybdenum cofactor, and the cofactor that is present in this is called MOCOs, that is all in a simplistic form. Now, I mentioned to you the enzyme in the oxidized form, which is the molybdenum 6 form, can convert the substrate to the to oxidation. When the enzyme in the reduced form, when it is 4 plus, it can reduce the substrate to the reduced one. So, therefore, these enzymes act as oxidoreductases. Now, let us look at that a little more clarity, what does it mean. So, take an enzyme, a model compound. So, a model compound is shown over there. So, you have dioxo molybdenum with dithiocarbamate, DTC is nothing but dithiocarbamate, as you can see from here, and this is a molybdenum 6 compound. And this molybdenum 6 compound in presence of the triphenyl phosphine will react, and triphenyl phosphine will try to reduce this and plucks out the one of the oxygen to become triphenyl phosphine oxide. You know, in triphenyl phosphine you have an empty orbital, it is basically a Lewis acid which can pick up the oxygen over there. So, therefore, triphenyl phosphine has got a pair of electrons which will accept the oxygen in the form of not along with the electrons, and the electrons will go to the molybdenum, because triphenyl phosphine will go to the triphenyl phosphine oxide, where the phosphine in the phosphorus is in 3 plus oxidation state, and the phosphine oxide, the phosphorus is in the plus 5 oxidation state. So, the 2 electrons lost. So, those 2 electrons are gained by oxygen. So, therefore, triphenyl phosphine oxide. So, therefore, O is taken not as O2 minus, then O as 2 plus, the 2 electrons are coming here. So, that means the 2 electrons left over here are given to the molybdenum, and the molybdenum becomes molybdenum 4. Now, you can see that out of the 2 oxos, 1 oxo is gone, and now you have only 1 oxo, it is molybdenum 4. And molybdenum 4 is a very reactive species, and little amount of molybdenum 6 present in that can react. So, let us call this molybdenum 6 as A species, molybdenum 4 as B species, then this A plus B will give a 4 oxidation, 6 oxidation, and together is a 5 5. So, 4 plus 6 10, 5 plus 5 10. So, you get a molybdenum 5 with a bridge oxo. Okay. And this is also very susceptible for water reaction. When the water is present, it can even form dioxo, and it can go back to the molybdenum 6. So, you can see molybdenum 6 going to molybdenum 4, going to molybdenum 5, going to molybdenum 6, etc. So, this is what I mean by the shuttling between the molybdenum 4, 5, 6. This has to be done in a very controlled fashion by the enzyme. If it does by controlled fashion by the enzyme, then it can do oxidation reaction in one stage, reduction reaction other stage. But if the enzyme is not surrounding the thing, then it can happen this one. So, this is a thermodynamic pit. So, formation of this, once it forms mu oxo dimolybdenum 5 or mu dioxo dimolybdenum dimer, both of these are dangerous. So, that means protein will bind to this and prevent the formation of such dimer, either this kind of dimer, a monobridge dimer or dibridge dimer. That is the beauty of the enzyme in this. So, that is where we can see the modal complexes. So, in the modal complexes, how would you try to make the protein mimic? You make a bulky groups, and that is where you can see that. So, bulky groups are put over there, and therefore, you can do phosphine reaction, triphenyl phosphine oxide, okay, etc. And then to reverse this, put dimethyl sulfoxide, will go to dimethyl sulfide. You can see that. So, in one direction it will go phosphine to phosphine oxide, and this one in the other direction you put the dimethyl sulfoxide, that will give the oxygen and give this one too. So, this is basically explained over there by this kind of a reaction, one electron reduction, one electron oxidation, another electron reduction, another electron oxidation. So, essentially this we would like to say that the molybdenum 6 to 5 to 4 and the 6. So, here it is 4, then 5, then the 6. So, if you put the reverse, 6 from 5 to 4. So, when you have a dioxo, it is 6, when you have monooxo, it is 4. If it is monooxo plus a sulfide, double bond sulfide, again it is plus 6. So, it is understandable that. Now, you understand that how these enzymes are able to act as a oxidoreductases. They are able to act as oxidoreductases because the enzyme can easily convert from 6 to 4, molybdenum 6 to molybdenum 4 and back to molybdenum 4 to molybdenum 6 by giving away the oxygen or by taking out the oxygen from and to the substrate. This is the essence of the whole thing. So, this essence now I will explain you through few examples. I have already given you essence. Now, dimethyl sulfoxide 2 protons 2 electrons give dimethyl sulfide, and you can make the reverse also if the enzyme is in reduced state. Enzyme is oxidized state, you will go in this direction, enzyme is in the reduced state, you will go in this direction. Sulfite oxidase, that is enzyme in the oxidized form, sulfite go to sulfate. If the enzyme is in the reduced form, the sulfate to sulfite. Similarly, aldehyde oxidoreductase, so aldehyde to carboxylic. Okay. So, you can go from carboxylic to aldehyde too. So, in all these cases, what I want to tell you is that the enzyme can undergo oxidation and reduction. Concomitantly, the substrate will go reduction and oxidation. So, the enzyme if undergoes oxidized, the substrate will be reduced. If the enzyme is reduced, substrate is oxidized. That is all. So, same things which I have told earlier too, xanthine oxidase, xanthine dehydrogenase, aldehyde oxidase, this all I have explained to you earlier. Now, let us look at this basic principle or concept that we understood now by using a few examples. One of them is xanthine oxidase or xanthine dehydrogenase. Oxidase and dehydrogenase are one and the same. So, xanthine oxidase during the reaction, you will see in the next slide, it will generate some reactive oxygen species like superoxide and etc. So, these enzymes play an important role in the catabolism of purines in some species including humans also. And you can see the whole structure of this one. This is a bovine xanthine oxidase. So, in this bovine xanthine oxidase, the red one is what? This is the molybdenum, this flavin adenine that cofactor, the flavin containing cofactor. Okay. And then the one which is in orange color, this is the iron sulfur cluster, and this one which is in the form of molybdenum cofactor. Okay. And this is the salicylate part, and this is before the enzyme in the resting state. So, this is the structure in the enzyme resting state. Let us recall or recapitulate what does the xanthine oxidase do. Xanthine oxidase catalyzes hypoxanthine to xanthine. You see that hypoxanthine to xanthine will happen. There is no CO here, the CO has come. And then it can do one more reaction also, xanthine to uric acid. So, you see the xanthine and the uric acid. So, uric acid has one more CO coming here. So, that will become xanthine to uric acid. So, from hypoxanthine to xanthine, an oxidation by one oxygen, and xanthine to uric acid is by oxidation by one more oxygen, totally 2 oxygen oxidation from hypoxanthine to uric acid. And this is where the xanthine oxidase, hypoxanthine, okay, and xanthine oxidase can generate the O2 minus, and this O2 minus can react with NO and give the peroxynitrite. Okay. So, as we have seen, xanthine oxidase can give a superoxide radical, and this superoxide radical in turn can react with NO, give peroxynitrate, which is all these are dangerous species. And of course, they can also get redox things by other things, and on one side you can have uric acid, as you can see over there. Okay. So, therefore, xanthine oxidase can also act as certain other species like purines, pterins and aldehydes. So, for example, it efficiently converts 1-methyl-xanthine. 1-methyl-xanthine is a metabolite of caffeine in the body. Caffeine, when you consume, then it metabolizes, that will give 1-methyl-xanthine. That will convert to 1-methyl uric acid. But suppose if the system has got 3-methyl-xanthine, okay, that will not get reacted, because the orientation is also important. So, that is where the enzyme reactions are both position specific as well as stereo specific, and that once again you can see that. So, under certain circumstances this can create the superoxide, and that is where the reaction is shown over there. Okay, xanthine oxide. So, let us look at the mechanism. So, first of all, the xanthine oxide, the oxidase, xanthine oxidase, what do you have? Xanthine oxidase has got 1 to 1, 1 pterin and 1 molybdenum center. This will react with the substrate. What is the substrate? Hypoxanthine. Okay. You see that the way that it reacts, and there are certain groups which I will show you in the next slide how they are supporting, and this undergoes a reaction over there from this oxo, and this will bind to the molybdenum. So, when it binds to the molybdenum, it is starting from 6 will go to the 4, and with 1 electron and 1 more electron will go back to the 6 and releases the product. When it goes here, the P is nothing but the product. Okay. So, product is what? Oxidized form. Okay. So, hypoxanthine to xanthine, then xanthine to uric acid. So, this we know already. So, now again back to this. So, therefore, you have an enzyme is ready for the next cycle. So, I just showed some examples. You can sit and look at hypoxanthine to xanthine to uric acid. So, allopurinol to oxypurinol, okay, and all of these are going from the substrate to the oxidized product to further oxidized. So, in this, how do we know this binding thing? This binding thing has been determined by using Endor experiment, electron nuclear double resonance spectroscopy, because it has the electron and there is a proton nuclei, you look for a coupling. From that you can get the distances. So, from the molybdenum to this carbon you can get the distance. So, therefore, you can fix how far it is, from that you can get whether it is bound at the molybdenum center, if so through what, etc., can be obtained. So, you can take it as granted. So, now let us look at a little bit more with clarity the same thing, but the reaction you can see that this is the molybdenum center having so many groups nearby, okay, and this is your cofactor part of it, and this is the dithiol thiolene thing. So, there is a glutamic, another glutamic, phenylalanine, arginine. So many kind of glutamic residues are there. So, these are all having some role or the other. We will look into that. So, you have the xanthine oxidase. So, therefore, this will activate by this glutamate to knock out this proton, and therefore, this becomes O minus, and that will be attacking the center, and this when it attacks center, then obviously this will undergo. So, how does it know this position? This knows this position because this particular substrate is held by this glutamate on one side, arginine on the other side. So, all through the hydrogen bonds. So, the hydrogen bonds extended by the side chain of this glutamate and side chain of this arginine will recognize and position the substrate exactly at this place, so that O can attack on this. So, let us take that O attacked on this, and when it is O attacked, there is one more activity, that this glutamate will again give a proton, provide a proton. So, you get some kind of an intermediate, and that will lead to the kind of a species you see that. So, that means now the oxygen is ready to go from molybdenum to the substrate, then go from hypoxanthine to xanthine. Okay. And this can happen with the 2 proton 2 electron, and in this case it is already xanthine. So, xanthine to uric acid you have. So, xanthine to uric acid. So, the xanthine recognized by like this kind of hydrogen bonds, and the attack by this will give, and then finally. So, the first one is the attack of this oxygen at this particular center, the molybdenum center, and that is activated by removal of the proton, and that will bind to this particular center, and then the, and how does it know? Because it holds this particular substrate in this particular fashion. So, finally, uric acid. So, you see that there is a lot of role of these amino acids. So, they are not directly bonded to your cofactor, they are the outside. So, that is what we refer as the secondary interactions. Now, let us look at another enzyme in this oxidoreductase category, molybdenum containing enzyme, that catalyzes the reduction of dimethyl sulfoxide to dimethyl sulfide. So, dimethyl sulfoxide, dimethyl sulfide. So, this particular thing is a 1:2, one pterine, other pterine, and the MOO with one of the ligand. So, as I said, these enzymes can undergo oxidized form, molybdenum 6, can undergo reduced form, molybdenum 4. If you take both the center overlay, you see that is so perfect with very little changes, That is why the enzyme is not taking too many changes, and enzyme is able to accept both the molybdenum 4, molybdenum 6 in that core, and undergoes exchange between 4 and 6 very facile. Therefore, these enzymes are able to act as a oxidoreductase enzymes. So, this is how the cofactor is inside buried in the DMSO reductase. So, this part is a cofactor, these are all interactions, etc. You can sit and have a look at, that is not very important in this. Now, DMSO oxidase, DMSO reductase. So, you have the 6 condition, the molybdenum 6 oxidation state, which will have about minus 150 millivolts. In presence of this serine residue, this will undergo redox facile redox to plus 37. So, and therefore, and now that will be easily converted to the OH, and then you get into the plus 80. This is very nice positive potential, go back to the from 5 and then to 6, and at this stage. So, this is all the resting enzyme stages, this is the active enzyme. So, from dioxo molybdenum 6 to serine bound to one more electron transfer kind of thing to 5, then to 6. Okay. So, finally, this is ready for the binding to the DMS, because the oxidase will oxidize the substrate. So, DMS can get oxidized to DMSO, and the DMS will bind at the metal center, and at this metal center then you have the oxygen, and that oxygen, which is this one, will go to the DMS and will go as DMSO. So, in the reductase part, let us start from this particular thing where the DMSO is bound, and you can see the changes happening, or we can take even the pre-form, the prior form of this, the molybdenum with serine, DMSO, and the DMSO binds over at the molybdenum center. Okay. And then this again it changes its redox potentials, also the electron transfer reaction, then it will go to the 6. Okay. And then it throws out the DMS, and then takes the oxygen, and by taking the oxygen it will go into the 5. So, that further redox process 5 and then 4 get back to the 4th state. So, oxidized and then reduced. So, therefore, that is where the thing is that. So, therefore, in one case the DMSO, DMS is oxidized to DMSO. In the other case, DMSO is reduced to DMS. Okay. So, as you can see over there, the type of reactions that are going. So, the 6, 5, then the 4, etc. So, that you can see. Okay, we can look at another example. Nitrate reductase means nitrate to nitrite. So, for a while you do not need to worry about this. Nitrate to nitrite, so it is a reductase. So, it has to reduce. It has to reduce means the enzyme has to take oxygen. If enzyme has to take oxygen means out means it should be in the reduced form. That is why. So, the molybdenum is molybdenum 4 cysteine. Nitrite, see this is NO3 can bind because it is not completely proven. So, it is put in the brackets and this will give away the NO2 and the molybdenum 6. Now, the molybdenum 4 is now molybdenum 6. This will not go back to this unless you have nitrite to nitrate part. So, otherwise there are enzymes which will reconvert this from the 2 electron, the 2 proton back to. So, therefore, so you add 2 electron and this one, so that will give the reduced form. So, you can get the reduced form and you can get the oxidized form. So, in this step the molybdenum 4 goes to molybdenum 6. In this redox cycle it will add 2 protons and it will add 2 electrons. The electrons are taken by the molybdenum 4 becomes electron taken by the molybdenum 6 and then it will go back to the 4. So, 4, 5 and 6, then it goes back to 4 and 6 as you can see. So, the involved is 2 protons and 2 electrons the water. Okay, let us look at another example which is sulfite oxidase. Okay. So, in the previous case what we have looked at nitrate becoming nitrite. So, in this case sulfide becoming sulfate. So, it is oxidase, that was reductase. This is from a model complex. Okay. So, this ligand is referred as MNT dithiolate complex. This is a perfect model for the enzyme and the HSO3 minus will give HSO4 minus and goes back. So, the molybdenum undergoes the redox process and the 6 to the 4. So, this is the model molecule. Of course, you have to regenerate back this. In enzyme it happens. Okay. So, let us look at the molybdenum center of the enzyme. This is an oxidase. Keep in mind whenever it is an oxidase, its molybdenum is in 6 form and it is a dioxo form or 1 double bond oxo, 1 double bond sulfide, either of these. So, now you have a molybdenum dioxo species, molybdenum 6. To this now you react with the sulfide SO3 minus. So, SO3 2 minus binding over there through its oxygen and it reduces. Then you go to the molybdenum 4 and then gives an oxygen to this, sulfide goes to sulfate and now the molybdenum is in not in 6, it is in 4 and this 4 is brought back to 6 by using a cytochrome C. So, cytochrome C will give 1 electron 2 times 2 1 electron and the 2 protons. So, this the whole thing will cycle. So, in the previous case it has gone to the 6, then you are bringing to 4. In the later case it has gone to 4, you are bringing to 6. So, therefore, this is done by the external protein systems. So, we have seen the oxidative type, oxidation type, reduction type, both of these we have seen very nicely in the example. Let us see one last example in this particular thing is the aldehyde oxidase. So, what will happen when the aldehyde oxidizes and when the aldehyde oxidizes, what is the oxidized form of aldehyde? Carboxylic acid. So, it is both electrons as well as oxygen. Aldehyde has got 1 C 1 O, carboxylic acid has got 2 O's. So, therefore, you need to add oxo species to that. So, this in this aldehyde oxidase you can see it is again a complex kind of an enzyme. So, you have a the FAD binding domain with a flammine adenine dinucleotide. So, which is shown in this stick form. This is a 40 kilodalton, and there is another part of the enzyme which is 20 kilodalton, and this has got the iron sulfur cluster, and this iron sulfur cluster is a 2 iron 2 sulfur cluster. This is 20 kilodalton, this is 40 kilodalton, and this whole thing is 80 kilodalton, and this domain where the molybdenum cofactor is there. So, this is one of the electron transfer center, this is another electron transfer center, this is the enzyme center, or in other words sorry, catalytic center. So, it is basically everything is together is enzyme, and this is the catalytic part of the enzyme. So, what is it doing? Aldehyde it picks up and converts into carboxylic acid. So, you can see, so it is oxidation. So, the enzyme in the oxidized form, which is in the 6 plus form, and this is bonded to that as we know, and in the aldehyde oxidase it is double bond O double bond S. Now, this will react with the aldehyde, and this is the water is activated by a glutamate, and that will have an interaction with this as you can see here, and that has picked up the proton, and you have the OH is transferred to the carbonyl center to make into a carboxylic species here, and this will go out, and then the enzyme will go into reduced form. Now, this has to be brought back here by other proteins like cytochromes etc., because cytochromes are well known electron transfer agents. So, we have seen a few examples, both oxidative type as well as reductive type, and nicely the enzyme goes through molybdenum 6 to molybdenum 4 and back. If you take a small molecule molybdenum complex, it will not do, because to molybdenum 5, when it forms a molybdenum 5, then it can interact with another. When it forms a molybdenum 4, it can interact with another molybdenum 6 and form molybdenum 5 oxo bridge. In presence of water, it can form even the dioxo bridge. So, there is a danger. So, small molecules cannot easily mimic this enzyme unless you do a lot of synthetic modification to prevent such dimer formation. Where did we see earlier one such dimer formation? The oxygen transport hemoglobin. There the iron porphyrin very easily gets dimerized if there is no preventing groups. So, the enzyme itself prevents. In summary, so let me say that the molybdenum enzymes, in summary, that we have looked at one enzyme which is nitrogenase, it is absolutely a reductase type. It can convert the nitrogen to ammonia, and many non-specific reactions are also there, and many places with a 2 electron 2 proton kind of reactions it is capable of doing. So, it can be used for probably if somebody is interested can isolate these enzymes from the natural source, arrest on some solid surface, and you can start using like a factory for synthesizing the products. The second part, we have looked at a huge range of reductase oxidases. You can see nitrite reductase part, pyridoxal oxidase, DMSO reductase, DMSO oxidase also, biotin sulfoxide reductase, xanthine oxidase, aldehyde oxidase. So, you see nitrite reductase, it will give nitrate to nitrite, pyridoxal oxidase, pyridoxal to pyridoxic acid, DMSO reductase to DMSO to DMS, dimethyl sulfide, biotin sulfoxide reductase, biotin sulfoxide to biotin, xanthine oxidase, xanthine to uric acid, aldehyde to carboxylic acid. These are the things. So, the first one is a very complicated, that the nitrogenase, and the nitrogenase requires a large number of 1 electron kind of things. The second kind of things are the trick of oxo transfer reactions. Oxo transfer followed by electron transfer followed by proton transfer. So, basically a proton transfer, electron transfer coupled with an oxo transfer. In other words, oxo transfer is coupled with proton and electron, so that the molybdenum can undergo +6, +5, +4 without getting dimerized, without getting the reaction being arrested in this. So, thus we conclude the part of the molybdenum enzymes by giving all these details and the mechanistic aspects. Thank you very much.